After introducing the torque and how it is used for static equilibrium systems, let's now focus on dynamic systems that are under a net torque that is not equal to zero. As an example, a cylinder which is being pulled by means of a rope which is wrapped around its circular circumference. Because of its shape, the cylinder is going to spin about its own axis of rotation instead of sliding against the surface. A similar example that can cause an object to slide is a block which is being pulled by means of a rope. The dynamics of this simple system can be studied using Newton's second law, which states the sum of the forces acting on the block equals the mass of the block times its acceleration. In a similar way, the spinning cylinder can be studied using Newton's second law for rotational motion. This law can be easily extracted from the sum of the forces equal ma equation. Instead of the net force, we are going to have the net torque. Instead of the mass, which is the linear inertia, we are going to have the rotational inertia, also known as the moment of inertia. And finally, instead of the linear acceleration a, we are going to have the angular acceleration alpha. As far as the inertia is concerned, remember that the linear inertia is the tendency to resist linear motion, and the moment of inertia is the tendency to resist rotational motion. Since the torque and the angular acceleration have already been discussed before, let's focus here on the moment of inertia. The moment of inertia is directly related to the mass and where the mass is located with respect to the axis of rotation. The moment of inertia I equal the sum of the point-like masses times r squared, which is how far those point-like masses are from the axis of rotation. Clearly, from the equation, the closer the mass to the axis of rotation, the smaller the moment of inertia, and the easier the object is going to be rotated. Using some calculus, and specifically the integration tool, we can derive the moment of inertia for known shapes. For a hollow cylinder or a hollow disk, the length of the cylinder does not matter. We have been able to derive the moment of inertia to equal mr squared, where r is the radius of the cylinder or the disk. Notice that all the mass is distributed in a form of a ring at a distance r away from the axis of rotation. For a uniform solid disk or a cylinder, the moment of inertia is found to equal 1/2 mr squared. Notice that the moment of inertia here is smaller than the hollow cylinder because some of the mass is closer to the axis of rotation. For a solid sphere, the moment of inertia is found to equal 2/5 mr squared. Notice that for a hollow sphere, which is not given here, the moment of inertia is equal to 2/3 mr squared. The moment of inertia of a thin rod about an axis that is passing through its center is found to equal 1/12 ml squared, where L is the length of the rod. However, if the axis of rotation is passing through one end, the moment of inertia is found to equal 1/3 ml squared. Notice the huge difference between when the axis is passing through the center and when the axis is passing through one end, 1/12 against 1/3. You can test this one easily by using a broomstick. Try to rotate it about an axis through the center and compare how easy that one is going to be when you try to rotate it about an extreme end. Finally, let me explain to you how the formulas for the moment of inertia about any axis other than the main one are derived. The moment of inertia about any axis is equal to the moment of inertia about the main axis plus the total mass times d squared, where d is the shortest distance from the center of mass of the object to the axis that we are evaluating the moment of inertia about. In the case of the rod, we have the moment of inertia about an axis that is passing through one end equals the moment of inertia about the main axis, which is 1/12 times ml squared plus the total mass times how far the extreme end from the center of mass, which is L over 2. Make sure you square it. This expression can be simplified to 1/12 ml squared plus 1/4 ml squared. The common denominator is 12, therefore it becomes 1 over 12 ml squared plus 3 over 12 ml squared. This is going to equal 4 over 12 ml squared, which is 1 over 3 ml squared, and that's exactly how the moment of inertia about an axis that is passing through one extreme end is derived. Remember that this equation applies for all other shapes.